Hello and welcome back to differential equations. Section 1.3, slope fields and solution curves. So the time before the last time, I talked about solving equations graphically, I think. Yeah, I did. And we are going to look at these concepts now and realize that every differential equation under the sun can be solved graphically. But it's going to be a little bit annoying to do that, so we still look for analytic solutions. Under the moon too. But under the moon doesn't include other planets. Just Earth. And we are going to Mars. And all of this is live, so let's keep talking about differential equations. And let Elon Musk think about the rest. You can apply for jobs. You only have 4 months in this course and then you're qualified. So from Calculus 1 you learned that derivative is the function which generates slopes of the tangent line. So if you understand that piece, then this lecture is done and you can literally leave right now. That's it. Derivative is the function which generates slopes of the tangent line. So what I have here is some function f of x, f of t, whatever. And then I can find the derivative y prime as f prime of x. So now, since this is on some x-axis out there, there's going to be a point A somewhere. And that point A will have a tangent line, and the slope of that tangent line will be f prime computed at A. You might also have a point B somewhere, which will have its own tangent line. So M2 is going to be f prime computed at B, and so on. So what I can do is, if I have the first order differential equation, I understand that dy dx or dy dt that I have there, y prime, is derivative. And everything else is this slope. So let me just take one of the examples. So now, actually you know all the letters, right? So you can read the examples that are in the book. I'll just pick something from homework. So from problem number 6, let's say. dy dx is equal to x minus y plus 1. So this is differential equation. And now you say, let's solve this. You're all excited because you love this course. And the only technique that you know is separation of variables, which means all y's on one side, all x's on the other. Do you see that you can't separate this one? Because if you move dx to the other side, dx is going to put parentheses around this and get the dx there, and there is the y that is trapped in there. Right? If you move the y as plus y to the other side, you can't move the x. There is no separation here. If every equation was separable equation, you would have the whole differential equations course to be, a section in Calculus 1. but it's not. So we cannot separate this. So we'll probably have to do some magic over there to solve this analytically. But we can solve this using what we call slope fields, and create the slope field and then draw solution curves through this. So let's see how that works. First of all, I'm going to understand that this thing over here is related to slope. So now I am going to say, let slope be 1, which means dy dx is equal to 1. I set that, right? I set the slope equal to 1. So what happens afterwards? Well, as soon as you have the dy dx is equal to 1, you can plug that in your differential equation and it becomes just a simple graph of a function. So now when I plug everything in, it becomes 1 equals x minus y plus 1. And I get y equals x. So what is this? Well, this is a very special line. Does anyone know the name of it? Yeah, it's fine. Good. And I can draw that line. So this is going to be my solution now. I can draw that line dashed. I missed. I draw that line. So this is your line y equals x. And what I'm going to do is I'm going to draw a little slopes, little line segments along that line everywhere. Well, that's just unfortunately again these little dashes. So I draw a little slope 1 line segments. That's the red stuff. Then I go and I set dy dx to be, let's say, 2. If I set dy dx to be 2, then we have 2 is equal to x minus y plus 1. So y is equal to x minus 1. Do we understand this? So all I did is I plug in and I just do some algebra or arithmetic. So 1, that makes it 1, y moves, this one moves, and that's it. I draw this line as well. Now x minus 1, that's going to be here. We know how to graph linear lines and all other lines in the galaxy. And along that line, I am going to draw little red slopes 2, because I picked slope to be 2. So in this case, slope is 1. In this case, slope is 2. So I'm going to draw, now slope 2 is slanted more up, so they're going to look like this. Let's say that's a slope 2. I draw slope 2 everywhere. And I'm going to pick, because I can, dy dx to be 3. That means the slope is 3. And I will still solve the equation. So 3 is equal to x minus y plus 1. So y is equal to x minus 2. So x minus 2, that's the next line down. And then m equals 3 is even more sloped. So we're going to make it a little bit steeper now. You can't do this exactly, but it actually gives you the idea of how the whole thing works. Just out of curiosity, let's try negative numbers as well, because we can. So let's do dy dx is equal to negative. No, let's do 0 first. Let's do 0 first. 0. So we have 0 is equal to x minus y plus 1, from where y is x plus 1. So it's going to be above. And it will have slope 0. What is the slope 0? Horizontal lines. Very good. All of these are straight lines. Different between straight and horizontal. There we go. So we have that horizontal piece there. And then let's do dy dx equals -1, which is -1 is equal to x minus y plus 1. That's y is x plus 2. Right here. And we draw slopes -1, which are 45 degrees slanted the other way. So they actually meet, perpendicular. And let's draw one more. -2. -2 is x minus y plus 1, so y equal x plus 3. And that would be here. -2 is even more slanted, so it's going to go like this. Again, you can't draw it perfectly, but this is, this is good enough. Now, when I was a student, I really wanted to know this and understand this, so I would actually draw about 10 to 15 of these lines. Now that I'm not a student and I'm lazy, I draw 6 because I know how this looks like. I developed that intuition just because I have gift. I never worked hard. It's just I was born that way. Yeah. The first comment was better than the second, right? Guys, just do as much as you can. I draw 6. You need to draw 12 of these to see how it works. What I see here, with the first 3 lines I drew, 3 just, I knew that the flow goes like this and goes like that. I don't know if you can focus to these red lines and just see, imagine a stream of water, right? And if you are to throw a leaf on top of this, these currents will take it. And that leaf can't go this way because you see that there is push that goes like this from this side. And there is a push that swirls and goes that side, right? And they merge into this middle one that is shooting straight at 45. So anywhere you throw a leaf here, it's gonna push it this way, it's going to push it this way, and this one is going to bend it, and it's going to push that way, and it's going to go like that forever. And you throw a leaf there, this one is going to give it to this one, and this one is going to push it this way. Now guys, there are other lines in between. Every single point of this infinite space is filled with these. We picked 1, 2, 3, but I can pick 1.5 and get the slope in between, which will make all of this smooth. When you drop the leaf on the top, it doesn't jerk its behavior from one slope to another. It has the smooth transition because all other slopes, all other infinity of slopes between 1 and 2 are in there to smoothly and continuously push that into this main flow in the middle. So now, I'm going to erase this, but now, if I look at this, I drop something. I drop something here. When I drop something here, the flow takes it. When I drop something here, the flow takes it. It follows these slopes. If I am able to figure out through fitting points on the line what these functions are, I have the solution to the differential equation in terms of a function. Well, it's clearly not a function, right, if you have multiple branches, but no matter where you drop it, it is going to follow these curves into this main channel. Does every single solution behave this way? Hell no. What do we see here? We see general solution. What's a particular solution? Particular solution, you will tell me, oh, I need a particular solution for 4, -6. Oh, 4, -6. Okay, let me see. 1, 2, 3, 4, 1, 2, 3. So this is 4, -6, and then I follow, right? And I start drawing from that point. So what is 4, -6? 4, -6 is a point where the leaf falls, and then the stream will take it from there. That's a particular solution, right? Because you drop it on a particular point, and a particular path that the leaf took is the solution. But you see infinitely many possibilities, and that's your general. So this slope field here, it's called slope field because every single little red line is a slope. This slope field is the one big general solution, and then you can pick a single path through that by giving me the initial point, and that single path will be the general solution to that differential equation. Yes?
How do you notice soon arc with 1? Like that is the breaking point between like each side? Or we just have to test like
no, you just it's the same like when you learn to graph the first time basic functions. Your instructor told you just graph points from -3 to 3, and you say, oh, now I have to, compute 7 points, right? It was a lot of work. Here's the 7 lines, right? So the answer to your question is I didn't. I just picked a value and I calculated, then I picked the next value and the next, and then I went back and did the others. You can make yourself a rule, calculate all of them from -3 to 3, and that's the end. But you clearly won't be calculating from -3 to 3 if I give you 4, 6 initial condition, because 4, 6 initial condition, 4, x value, is not from your -3 to 3. So you'll be computing maybe from 2 to 5 or 2 to 7, and then that 4 is in there, and they will give you the band of slopes around the area where you want to see what's happening. These slopes fields can be really crazy. So those of you took Calc 3, you know about slope fields and how they can be radial and you can spiral in and spiral out and do all kinds of cool crazy things. They can do all of that. right? And there are some really cool examples in a textbook that would literally take us ages to compute. The more time you spend on what you think are trivial tasks in this class, the more you will learn. So there are some really annoying problems that you can draw slope fields for. And if you have this particular, well, any textbook will have the examples. You can see the slope fields, and they show you, one of the paths, possible paths. This reminded me when I was a student of those maze puzzles, right, where you have to find the path. Well, this is technically that thing, except you don't have walls clearly stated. You are guided by the red lines, and you have to follow the flow. You can't go against the flow. That's technically what it is. Yes?
Kind of random, but I was just thinking, like, could you use this for, like, magnets and, like, charges to try to...
This is exactly what it is,
where it passes?
because this is a field.
Yeah.
Magnetic field is a field, the electric field is a field, and the forces that you're experiencing in that field are driven like this.
Yeah.
So this is exactly what it is. Okay. And these are your magnetic lines.
Yeah.
All right? That's exactly what it is. So this is what you would be computing, and because you want to know how magnetic fields look like, right? And that kind of stuff. So I'm just going to read this, and then you will just try to imagine what kind of horror would be to draw the field. But suppose the deer population P in a small forest satisfies the logistic equation dP dt is equal to 0.0225 P minus 0.0003 P cubed. Construct a slope field, and this is where you just stop reading, right? So you have, for this particular problem, we have 1 minute and then another 15 after that. For this particular problem, this is 26 in your textbook. You are talking about the change of population of deer in time, obviously. 0.0225 P minus 0.0003 P cubed. Oh no, that's P squared. P squared. So here is your differential equation. You construct the slope field in the same way. Nothing new. You say my slope m, which is dp dt, is 0 for the first one. So if it's 0 for the first one, you need to graph 0.0225 p minus 0.0003 p squared equals to 0. Well, that's going to be some kind of parabola opening downward, right? With the slopes 0 on it. And then you go with 1, which would be another parabola that will have slopes 1. That's also slope 0. I'm sketching. So it will generate slope field again. Except, so guys, this is not hard. It is annoying. You have to understand the difference between hard and annoying. You changing these numbers will change this value here, which you have to bring over and graph the parabola. All of these parabolas are going to open downwards because negative a on the squared term, so all of them open down. But look at the constants, right? The coefficients. So it's just, this is what the annoyance of the whole thing is. And this is why we employ Mathematica, and understand that we say construct the slope field. Right? It gives you the slope field. So maybe it was beneficial for you to do first 6 problems by hand to understand the concept, to brush up on the idea, slope field and derivative, the first derivative, tangent line, and all of that cool stuff. And then immediately switch to what you are actually going to use in industry, and that is software to generate a slope field. Because no one will be paying you to waste time, draw these things by hand, and then you put it in a, you do it on the college ruled paper by hand, and then you staple it to your $300,000 report. And tomorrow you play the guitar on station. Right? So, yeah, just do a few of these, try them. We can do another one if you want to. Anyone? Not saying?
So that would just be your answer, just.
Oh no, this ugly thing, no, because you will draw the beautiful.
Yeah,
Yes.
you need way more lines.
You will draw at least 6,
Yeah.
but shoot for 10 or 12 beautiful lines with perfect slopes of 0 and 1 and so on. And then and you can draw beautiful slopes if you have the proper paper, because slope of 2 is 2 squares up and 1. So you have the little, you know how the slope looks like, and then you just use the ruler and keep the ruler at the same slope, and then you just keep drawing little ones. So it's just, how particular you want to be about these things, how well you want to learn. That's it. I know this guy's not messing up. Look at the protractor right there. That's the next level stuff. No, I'm serious, and it's good. But you still have the wrong notebook, so kind of balances it out. All right, cool. Am I done for? Yeah, I'm done for today. The next lecture is separable differential equations, which is what you already know. So the next class is going to be probably 1.4 and 1.5. Probably. So just in case, do those 2 class preps, 1.4.